describe the lines as pointing, radiating radially outwards from the positive charge and radiating radially inwards into the negative. Is it just possible people mute themselves? So we describe it as the lines. The lines give us information about the direction with which the force is acting. It tells us the direction with which the force will act on the positive charge. So when the positive charge is placed within the vicinity of this charge, the lines of force around it will tell us in what direction that positive charge will go. And since it will repel, we'd expect it to move away from the central charge. And we'll expect it to move a positive charge to move towards a negative charge, as shown in this diagram. That is, since the lines of force for a negative charge direct radially inwards, then it's easy for us to imagine that the charges will move, a positive charge rather, will move towards the negative charge. And in this scenario, let's talk about a +6 charge and a -3 charge. That is two opposite charges and of unequal magnitude. So all the lines of force that the -3 is entitled to has already been captured, has been occupied by the positive charge. So around this negative charge, you can this negative charge is now appearing to be redundant. You cannot, because all the lines of force have been captured by the nearby positive charge. So when we talk about electric field intensity, we are talking about the electric field strength. I tried giving us a scenario in the last class where I spoke about you having a bulb. Was it the last class or the one before? Where if you imagine a bulb where the rays of light emanate radially outwards, when you are closer to the bulb, you enjoy the brightness more than when you are far away. And a way to analogous way to mimic the brightness is that when you come with a certain area, when you come with a sheet of a certain area, now we're in 2D. So our area will be a form of line. So this green sheet, you imagine it to be a sheet of paper having a certain area. And as you are bringing it closer to the bulb, more ray lines will cross through the paper. When you bring it very close, when you bring the same paper very close, when you bring it closer, you can see it is being intersected by 2 lines. When you bring it a little bit closer, it will be intersected by 3 lines. When you bring it closer, it will be intersected by more, depending on the resolution with which the lines have been drawn. So let's look at the example we have here. We have an example here that says a unit charge Q creates an electric field. What is the magnitude of the electric field strength at a distance 30 centimeters away from the charge? It says a unit charge Q. Well, we say a unit charge. Unit means 1. A unit charge Q, that is Q has a charge of 1 coulomb. A unit charge Q. So we can imagine a unit charge Q, a certain unit charge Q that has its line of force also radiating radially outwards. And the question is asking us that what is the magnitude of the electric field strength. You are not interested in the direction now. The magnitude of the electric field strength at a distance 30 centimeters away from the charge. So that we should remember that the electric field strength is defined as K of the certain Q divided by R squared. So the question says at a distance 30 centimeters. So at this point, our R is equal to 30 centimeters. And we should also, that is at a certain distance, what is the field strength? So just like I've said over and over, when you move closer to the charge, or when a charge body moves closer to a charge, it will experience greater force, be it attraction or repulsion. The closer two charges are, the greater will be the magnitude of the force between them, be it attraction or repulsion. And at a certain distance from a charge, the field strength will increase when you move closer. So when you move closer to a charge, the field strength will increase. When you move closer to a charge, the field strength will increase with following the inverse square law. And when you move away from the charge, the field strength will also reduce, obeying the inverse square law. So we should always remember that we have specified charge to be in coulomb. Then the distance R should also be specified in SI units, which is 0.3 meters. So then we should come here and say that our K, which is approximately 9, is 0.3 all squared. And whatsoever you have, the unit is Newton per coulomb. And for the next example, the other example says that what is the magnitude at 90 centimeters? So what that is saying that when R is equal to 90 centimeters, R can be said to be equal to 0.9 meters. Then E can be said to be K times Q is still a unit charge divided by R squared. And the unit is also in Newton per coulomb. So if you, at your leisure time, I suggest you attempt, you should have, I think 1 times 10 raised to power 11 for a 30 centimeter, and 1.1 times 10 raised to power 10, both Newton per coulomb for the second example, which is considering 90 centimeters away from the charge. So now let's move on to charge distribution. So we've been talking about a charge, but now let's now picture it out like now we having a system of charges. We having a group of charges distributed over a certain material. The material can have the form of a line, just like we have here. It can also have the form of a plate, like we have here. And it can also have the form of a yam tuber, as we have here. So when we have the charge distributed along this line, if it is such a way that the charges are so close, in which the distance of separation between the charges is smaller than the distance from where the electric field is to be calculated, then it requires that we consider the charge distribution. So when we have a certain length L on the x-axis, we can take a certain distance dx and and try to determine what is the electric field that this distance dx is contributing to the particular field. So let me say we have a particular point here. This particular point P is away from this particular continuous charged line L. What is the electric field that this particular that will be experienced at this point because of the presence of this continuous charge found on this line? To determine that, we need to cut all these, we need to cut this length into small fragments, dx. And we'll cut them into small fragment dx. Then we'll now find out what is the contribution of each of those small fragments to this particular point P. When we determine the contribution of each of the fragments to the to this particular point P, then we can say that we have found the contribution of this of all the charges distributed on this line to this one, because electric field is a vector quantity, so it is easy for us to add up the contribution of all the elemental charges to a particular point. Similarly, when we have charges distributed on a surface, we can cut the surface into small areas, like ds or dr, small areas, and determine what will be the contribution of this particular area to the particular point of interest, to the particular point where the electric field strength is to be investigated. And also for a particular volume where we have the charges all around it, we can cut the particular volume into small fragments, small volumetric fragments. And those fragments will determine their contribution, the contribution of their electric field strength to the certain point P. And by knowing the contribution of each of them, and we add those contributions together, then we can say that we have the contribution of every elemental charge of this entire body to that particular point. So, just like I've said, the total electric field at point P created by continuous charge distribution can be evaluated by 1, divide them into small elements. 2, calculate the electric field due to each of the elements to a certain point P. So this is what the text in this page is referring to, this diagram at this corner. This is a particular body which contains many charges distributed all over it, and now the body has been cut into several fragments. So and each of the fragments, if it's a certain volume V, then each of the fragments can be said to be dV or delta V. So for each of those fragments, their charges can be said to be delta Q, because so that the entire charge in this body will be called Q. So at a certain point P, which is at a distance r from each of the delta Qs, we can calculate the electric field strength at this point. So the R will depend on each of the points. So the R will vary based on each of the elements. So by knowing the contribution of each of them, we can easily add them up because they are vectors and say that we have determined all the contribution of all the charges to this certain point. So let me do this one. So let's assume we have we have cut them into small fragments. We'll keep having different R for each of the DQs, for each of the DQ, and we'll calculate E, delta E. So there will be small electric fields. So each of them will be contributing a certain delta E. Each of the elemental charges will be contributing a certain delta E as electric field at point P. So each of the delta Qs will be contributing a certain delta E at a particular point P, which is R distance away from which is R distance away. That is, R is the distance of separation between that delta Q and the point P, where we are interested, in knowing the electric field strength. So now, if we know all the delta E's, our black pen, come on, our E, which is a vector quantity, can be said to be equal to a summation of all the delta E. Or let me say delta EI. So for all the delta EIs, let's say for I under the summation. For all the delta E's, we add them together. So to determine delta E in this equation, we use this particular equation, which is just as the equation we are used to. The equation we are used to, as said originally, as defined as E is equal to AQ over R squared. If you look closely, it's still, there is nothing really new. It's just that we are trying to make them useful for this scenario. So this is the equation that we are used to. And now we are now interested in small fragments of Q, which will contribute small fragments of delta E to a certain point P, which is R away from the charge Q. So when we expand this particular summation, then we have the last equation we have here. So when you decide to make your delta E, and you decide to make your delta E to be equal to AQ, then what you have will be the last equation. Fine. I will move into slow. Okay, let's double up. So, since the charge distribution is continuous, it's not easy for you to use summation to add up when it's in a continuous surface. So just like we have in this, just like we have in this line, it's saying that we add up all the elemental charges here. Fine, it's good, but there are easier ways to do things like that when the distribution is continuous. And when distribution is continuous, our mathematicians prefer that we don't use summation anymore, but to use integral. So in place of using integral, that is when we have cut the yam, or we have cut this volume into very, very tiny elements of the Q, and it is continuous, then instead of us adding each of them up, a easy way to go about it is to integrate. And we integrate with respect to with respect to the Q. And since we said they are uniform, we would expect that all the small cuts, that is what we have, the big volume that we have cut into small pieces, the cuts are equal and the charges in each of them are equal. Then this expression can be said to be valid. So if you look at it very closely, you'll see that it is still resembling that particular equation that is friendly, that particular equation that says E is equal to AQ over R squared. If you compare these two equations, you see they are still the same. When you integrate the Q, you should have Q. You should have Q. But some mathematicians will still say Q plus C. But in this scenario, C is 0, so you should have Q. So let's move forward. So the integration over a vector operation over the entire charge distribution, the integration is a vector operation. So when we are integrating, we should also consider the fact that we are dealing with vectors. In continuous charge distribution, it is more convenient to use the concept of charge density. So instead of us to say, instead of us to talk about all these DQs, it's easy for us to say that a certain charge Q, when a certain charge Q is all over this line, we should be able to talk about a particular quantity called lambda, which is equal to that certain charge Q over this entire length. So this charge Q, this lambda is the linear charge length, but we have a certain length and we know lambda, then easily we can determine the entire charge. So, and this particular surface can also talk about the surface in terms of sigma. Sigma equals to, so a certain sigma to be equal to the charge over area, and rho to be equal to charge over volume. And the unit here is coulomb per meter. This is coulomb per meter square. And this is coulomb per meter cube. So you can see that it's very smooth and straightforward. So, and a simple way to define them all is to now talk about that Q for a certain volume, for a certain length, will be lambda L, which is B in coulomb. Q here will be sigma A, which is also in coulomb, and Q here is equal to rho V. So what it's telling us is that when you know the charge density on a particular line, you know the linear charge density on a particular line, and you know the length of that line, then easily you can tell us the charge of that particular line. Or you have a certain plate and you know the charge density of that plate, that is for any particular area, this will be the charge. So that is what the sigma here tells us. The sigma tells us that this is the charge I contain per area. So when you know the area of interest, then easily you can determine the charge that that certain area possesses. So let's move forward. Okay, I think let me look at the chat box. Some people just come here, they don't listen, they come here to write their name and matric number in the chat box. And the people that have reasonable questions, their messages will be clouded, will be drowned. Okay, electric field intensity and electric field strength, they are the same thing. Somebody is asking, I would like to know the difference between electric field intensity and electric field strength. They are the same. What I've just said, somebody is sending magic number here. Wow, that's shameful. Okay. Let's talk about motion. Motion of a charged particle in a uniform electric field. When we have an electric field, it means that charge, the influence of charge can be experienced, the influence of electric charge can be felt. And when we have another charge in electric field, what are all these? I said, don't send your matric number to the chat box. What's all this? Is it until I start noting your matric numbers and start counting you as disturbers in the class? Sorry, please. So, so the motion of, so when we have a particular charge, when we have a charge in an electric field, or have a charge in an electric field, it should experience a force. Just like when we have two charges at close range, they should experience significant force. Now let's picture this to be an electric field. This plate is positive, this plate is negative, and the plate is separated by a distance d. Then easily we can say that a certain field E will be experienced, and the line of the field will point from the positive to the negative. So when you put a positive charge here, you would expect it to move in the direction of this arrow. So now, when we have a particular charged particle, if it is positive, we would expect it to move to the right. If it's negative, we would expect that charge to move to the left, towards the positive plate. Before it can move, it must have experienced a force. That is Newton's first law, right? Before it moves, it should experience a force. And when the particular body is here, which is charged in an electric field, it should experience a force. So that is Newton's first law. And Newton's second law says that when it experiences a force, it should accelerate. So Newton's second law explains that when it experiences a force, it should accelerate. And that should lead us to defining the electric force. In the past, we have defined our electric force to be KQ1 Q2 over R squared. And we have now said E to be F over Q. Or in this case, let's just say Q2. So it is easy for us to now define our electric force to mean Fe is equal to QE. Because force, electric force divided by force per charge, which is Newton per coulomb, gives us the electric field strength. And we should also recall that from Newton's second law, F is equal to MA. Since F is equal to QE and QE and F is equal to MA, then easily we can say that QE is equal to MA. And we should also remember that the electric field strength is a vector quantity, just like the acceleration. So when a charged body is placed in an electric field, when the charged body is placed in an electric field, we expect it to experience electric force. And since it is experiencing electric force, which is a valid force of nature, then we expect it to accelerate. The direction of acceleration depends on the nature of the charge. So if it's a positive charge, it will accelerate to the right, and if it's a negative charge, it will accelerate to the left. So that is one. And two, the magnitude of the acceleration depends on the magnitude of that charge itself. So if it is a charge of small magnitude, the acceleration will be slower than if it's a charge of a large magnitude. Also, the acceleration also depends on the electric field that is present, the electric field strength, the electric field intensity. If it's large, when E is large, we would expect the acceleration to be higher. And it also depends on the mass of that charge, because the charge is not massless. The electron has a mass, the proton has a mass. So the charged body, in this case, forgetting if it's a proton or an electron, a charged body which has a net charge that is not zero, the charged body would accelerate based on its mass. A smaller mass would accelerate easily than a large mass. Because when the same force is applied, when you are pushing a wheelbarrow compared to you pushing a truck with the same force, one would accelerate faster than the other. So I think I've been able to explain the concept that for two plates of opposite charges, an electric field is set up, and when the charge is placed in an electric field, it accelerates. The direction of acceleration depends on the nature of the charge, because positive charge would move in the direction of the line of force, while negative charge will move opposite direction of the line of force. Let's move forward. So just like we've shown in the previous diagram, this particular body is now just turned, we are turning it the other way. So now let's think about this plates. This is a positive plate and negative plate. As usual, you see the line of force is pointing from positive to negative. As usual, line of force is pointing from positive to negative. When a positive charge is placed within this region, it will move upward. When a negative charge is placed within this region, it will come downwards. So now let's think about, so now we have this to be an electric field, that is electric force can be experienced. Now an electron, which is negatively charged, don't let us mention electron, like a body which is negatively charged is entering this region. You will expect that negative charge to come downwards. So, but the negative charge was coming in this direction. If there were not, if the electric force here disappears, if we turn off the electricity supply, if we turn off the electric field, between these plates, this particular body would move in a straight line. It will continue to move with a certain velocity VI in direction I. So the velocity will be VI, that is, it will have a constant velocity and the direction will not change. But now, the body has been coming from here in a straight line, but when it gets to this region, when it gets to this field, this region where electric force can be experienced, it will continue to move in this direction, but in addition to moving in the positive X direction or in the I direction, it will also begin to go downwards. So the motion will now have two components, the X direction component and the Y direction component, because as it's moving to the right, the motion, the force, as it's moving to the right, it is moving to the right undisturbed. But because of the presence of electric field, the electric field that is set up here would push it downwards. But the way with which it would push it downwards would not affect its horizontal journey. So it will continue to move in its horizontal journey. It will continue continue to move to the right with a velocity VI. But in addition to that, it will also begin to move downwards with a velocity that we are going to see very shortly. So, as described there, the displacement X in the horizontal direction is a product of the horizontal components of velocity and time taken. So for it's moving, this particular body, let's assume it's moving with a horizontal velocity UX. If it's moving with a horizontal velocity UX, at a certain time t, it would have covered a distance x. UX, which is velocity times time is distance. So at a certain time t, it would have covered a distance x. Because of the presence of magnetic field. Excuse me. Because of the presence of the electric field, because of the presence of electric field, charged body, the negative charged body will begin to move downwards. So that is the origin of this curved part. So this, because of the presence of the electric field, you can see that is curved in this direction. And when you look at it closely, you'll notice that if you look at this line, the way it started bending to the downwards, and later it's bended rapidly. That is a sign of acceleration. If it did not accelerate, it should have come here in a straight line. But because of the acceleration, that is why it is curved in this parabolic way. So, two things. It is traveling to the right with a velocity UX. That is not disturbed. The other is that it is accelerating downwards. That is, the velocity with which it is coming downwards will increase. And that will amount to this curved part. So when you stand at this particular point, when you stand here, let me draw you. When you stand here and you view this particular charge, when you stand here and you view this charged body, you will see it move in a straight line. You will not notice anything. You will see it move in a straight line, undisturbed, not accelerating. But when you stand here, oh, no. The tablet I'm using is struggling with charging. So it may go off anytime. And when it does, I will continue on the computer. So before it goes off, I wanted to draw you at this side again. When you stand here, so when you are the blue guy, what you will see is the electron coming in this direction. Not just coming, accelerating downwards. You will not notice it coming towards you. What you will see is that it is moving downwards, accelerating downwards. That aside, but when you are looking into the screen, that is when you can see the true picture, that it is moving to the right and also coming downwards. It is moving to the right with a constant velocity, and it is moving downwards with a certain acceleration. What is this acceleration? We have defined this acceleration in the previous slide to mean QE over M. So when we say acceleration to define as the charge electric field over M, then easily we can use some of these laws in the basic kinematics, basic mechanics, to say that, let me see if I will understand, to say that y equal to half a t squared. So when you say y is equal to half a t squared, then you should no longer be surprised of where we got our a, which is QE over M. So from A is equal to QE over M, and we know Y is equal to half a t squared, then the origin of this expression is out. And we know T, which is time. T, which is time. In primary school, my teacher taught me that time. Apologies to those that did not attend primary school class. Time is equal to distance. We used to call it G over speed. I'll call it S. But along the line, things began to change, and they changed for the better. So, but to adapt it into our scenario here, time is equal to distance